Settle in. This is Unintended Consequences, episode 51 for July 7th, 2026. Today's profile: a policy that did the opposite of what its designers intended. In the summer of 2003, as the first phase of reservoir filling behind the Three Gorges Dam raised water levels more than 100 meters along the Yangtze, residents near the town of Wushan watched entire hillsides begin to move. What made that rise so consequential was the sheer speed at which the water was added. The reservoir did not fill gradually over decades, but instead climbed more than 100 meters in a single season, placing an entirely new load on slopes that had never carried it before. People living on those slopes noticed the ground shifting under fields they had worked for generations. And the movement was not limited to one hillside, but appeared across multiple locations at roughly the same time the water reached its new elevation. Cracks opened in fields that had been farmed for generations, and small slides sent mud and rock into the rising water. Those cracks were not random surface fissures. They formed where the added saturation reduced the friction that had previously held soil and rock in place, allowing gravity to pull material downslope once the water table rose. The small slides that followed carried loose debris directly into the reservoir, showing how quickly the change in moisture could turn stable ground into something that behaved like a fluid. The structure had been built to tame floods and generate electricity on a scale never attempted before. Instead, the weight of the water itself started reshaping the surrounding geology. The original calculations had treated the reservoir as a static body of water whose primary effects would be downstream. Yet the mass itself, once impounded, began to press on the underlying rock in ways that altered local stress fields almost immediately. The idea of a massive dam at the Three Gorges site dates to Sun Yat-sen's 1919 proposal to improve navigation and irrigation on the Yangtze. That early vision already recognized the river's dual character as both a lifeline and a recurring threat, and later planners kept returning to the same narrow stretch of valley because the topography offered a natural constriction where a single barrier could influence hundreds of kilometers of river. Chinese leaders revisited the concept after devastating floods in 1954 that killed more than 30,000 people and displaced millions. Those floods demonstrated that existing levees and smaller reservoirs could not contain the volume of water that arrived during an extreme monsoon. So the memory of that single year kept the larger project alive in official planning documents for decades afterward. By the 1980s, rapid economic growth created urgent demand for electricity and greater protection for the densely populated middle and lower Yangtze basin. Industrial output was expanding at double-digit rates in coastal provinces, and planners calculated that the gap between supply and demand would widen unless a single large source could be added. At the same time, the growing cities and farmland downstream needed assurance that another 1954-scale flood would not erase years of investment. Premier Li Peng, a hydraulic engineer by training, championed the project as essential infrastructure that would both prevent catastrophe and supply roughly one-tenth of the country's power needs at the time. Because he understood the arithmetic of reservoir storage and turbine output, he could argue that one structure could deliver both flood space volume and generating capacity without requiring separate investments in multiple smaller dams. The National People's Congress formally approved construction in 1992, after years of feasibility studies that emphasized flood storage capacity of 22 billion cubic meters and a generating capacity of 22,500 megawatts. Those studies framed the numbers as complementary rather than competing. The same volume held back during peak flow could later be released through turbines, turning a safety margin into an energy asset measured in thousands of megawatts. At the scale envisioned, the dam appeared to offer a single intervention capable of addressing multiple national priorities simultaneously. The arithmetic suggested that one concrete structure, one reservoir, and one set of turbines could reduce flood peaks, generate electricity, and improve navigation all at once, which made the project attractive when budgets and political attention were finite. Construction began in 1994 at Sandoping in Hubei province. The site was chosen because the valley narrows there, allowing the dam to be anchored into bedrock on both banks while the reservoir extended upstream for roughly 660 kilometers once complete. The reservoir was filled in stages, reaching 135 meters in 2003, 156 meters in 2006, and the final operating level of 175 meters in 2010. Each increment added hundreds of millions of cubic meters of water, and the staged approach was intended to let engineers observe how the slopes and faults responded before committing the full load. Official reports at the time highlighted successful power generation that began feeding the grid in 2003 and the relocation of roughly 1.13 million residents from 13 cities and hundreds of villages. The relocation itself required building new towns on higher ground, new roads, and new farmland, all completed on a timetable that matched the rising water levels. Proponents cited reduced flood peaks downstream during the 2010 and 2012 monsoon seasons as early validation. Those seasons brought rainfall totals comparable to earlier flood years, yet the measured crest heights below the dam were lower by several meters, which appeared to confirm that the storage volume was performing as modeled. Some geologists and environmental researchers inside and outside China had warned during the approval process that the unprecedented water load could affect seismic activity and slope stability, yet the project moved forward with monitoring programs intended to manage those risks. The monitoring networks were designed to detect movement after it began rather than to predict exactly where or when a slope would fail under the new saturation conditions. Once the reservoir reached full capacity, the added weight of approximately 39 billion tons of water altered stresses on the crust beneath the 660-kilometer reservoir. 39 billion tons is roughly the mass of a 40-meter thick layer spread across the entire reservoir surface, and that layer pressed downward on rock that had previously supported only air and soil, changing the balance of forces along existing faults. Seismic stations recorded a measurable increase in small earthquakes, particularly along the Zigui and Badong segments of the Yangtze, with events clustered after rapid water level rises. The timing suggested that the added pore pressure in the rock reduced the effective normal stress on fault planes, allowing small slips to occur sooner than they would have under natural rainfall alone. On the reservoir margins, saturation of previously dry slopes triggered hundreds of landslides. The 2003 Qianjiangping slide killed 24 people and blocked a tributary. That slide occurred when water rapidly entered joints and fractures that had stayed dry for centuries, turning what had been a stable hillside into a mass that slid as a single unit into the reservoir. Further downstream, the dam trapped most of the Yangtze's sediment load, starving the river channel and coastal delta of material needed to maintain elevation against subsidence and sea level rise. Without the yearly replenishment of silt, the riverbed downstream began to erode, and the delta front lost the sediment that had previously offset gradual sinking of the land surface. Towns and farmland that had been relocated to higher ground sometimes found themselves on slopes newly prone to failure because the relocated communities themselves altered drainage patterns. New roads and house foundations changed how rainwater flowed across those slopes, concentrating water in places that had not been designed to carry it, which in turn raised local groundwater levels and reduced slope stability further. The combination of these effects, induced seismicity, repeated landslides, and sediment starvation arose directly from the decision to impound such an enormous volume of water in a tectonically active, steeply incised valley. Each individual process had been discussed in the feasibility studies, yet the studies treated them as separate monitoring tasks rather than as coupled consequences that could reinforce one another once the reservoir was full. Chinese authorities expanded monitoring networks and imposed seasonal water level restrictions to reduce landslide risk during the monsoon. The restrictions meant drawing the reservoir down by several meters before the heaviest rains arrived, which lowered the saturation level on the most vulnerable slopes, even though it also reduced the amount of water available for power generation at that moment. Some of the most unstable slopes received engineered stabilization, yet new slides continue to appear after heavy rains or rapid drawdowns. The stabilization measures, such as drainage tunnels and retaining structures, address the slopes that had already shown movement, but they could not eliminate the underlying change in groundwater conditions created by the reservoir's presence. The sediment deficit has required periodic flushing operations that temporarily lower reservoir levels, trading power generation and flood storage for downstream channel maintenance. During flushing, operators open the gates to let sediment-laden water pass through, which restores some material to the lower river but also means the reservoir cannot hold its full flood control volume or run its turbines at full capacity for those days or weeks. No reversal of the dam itself has been contemplated. Instead, the operating regime has been adjusted iteratively. Each adjustment is tested against the latest monitoring data, and the operating rules are revised again when new slides appear or when downstream erosion measurements exceed earlier thresholds. Today, the structure still supplies roughly 100 terawatt hours annually while providing measurable flood peak reduction, even as geological management remains an ongoing operational cost. The energy figure represents a large fraction of the original design output, yet the additional expense of slope monitoring, flushing, and stabilization was not part of the 1992 cost estimates. Interventions that concentrate enormous mass or force in one location can shift stresses throughout surrounding physical systems in ways that are difficult to model completely beforehand. When the mass in question is on the order of tens of billions of tons of water, even small changes in pore pressure or sediment supply can propagate through the landscape faster than the original models anticipated. When the scale of a project approaches the magnitude of natural geological forces, second-order effects on slopes, faults, and sediment transport become first-order concerns rather than minor externalities. The distinction matters because the same volume of water that delivers flood protection and electricity also changes the boundary conditions for every slope and fault within the reservoir's reach. Decision makers facing similarly large proposals today can usefully ask what existing stresses in the landscape or society will be amplified, not merely whether the primary objective will be met. The question shifts attention from the intended benefit to the pre-existing conditions that the new load will interact with, whether those conditions are faults, sediment budgets, or drainage patterns on relocated land. How might we test the stability of an entire system before committing to changes whose physical consequences cannot be undone? One approach is to introduce the load in smaller increments while maintaining independent observation networks that can halt or reverse the next increment if measured responses exceed earlier projections. And that's where today's story leaves us. If it changed how you see one everyday decision, that's the whole point. Pass it along to someone who'd appreciate it, and we'll be back tomorrow with another case. And if you'd rather watch than listen, find us on YouTube at Nerra Network, links in the show notes. And before you go, this show is part of the Nerra Network, a family of daily podcasts on tech, science, and markets, each one a short, sharp briefing you can finish on the commute. If today earned its place in your feed, here's your next listen. Planetarian Daily, daily breakthroughs in science, health, and longevity. Find every show free at nerranetwork.com. This episode used AI voice synthesis of my voice. Editorial selection and analysis are my own.